Let's take a look at a beautiful interaction between rectilinear and curvilinear geometry. Imagine an equilateral triangle, ABC, with a side length of exactly 14 units. Inside this triangle, we are inscribing a semicircle. We position it strategically so that its flat diameter lies flush along the horizontal base, AB, while its curved arc rises up and smoothly brushes against the remaining two sides, AC and BC, establishing two distinct points of tangency. Our objective is to determine the exact radius of this inscribed semicircle. To analyze this system, we rely on the core principles of symmetry and the properties of tangents. Because an equilateral triangle is perfectly symmetrical, a semicircle resting on its base and touching both flanking sides must be centered exactly at the midpoint of that base. Let's call this center point O. Now, if we draw a radius from O to the point of tangency on side AC, a fundamental rule of geometry comes into play. A radius meeting a tangent line always forms a perpendicular 90 degrees angle. This line segment instantly carves out a smaller right-angled triangle within our larger structure. Let's isolate this right triangle, which we can define by the vertex A, the center O, and the tangency point. We know two crucial things about it. First, because the original triangle is equilateral, the interior angle at vertex A is precisely 60 degrees. Second, because O is the midpoint of the base, the hypotenuse of our new right triangle is exactly half of the total side length, giving us a value of 7 units. The side opposite our 60 degrees angle is the very radius we are trying to find. By applying the sine ratio, we know that the sine of 60 degrees equals the opposite side over the hypotenuse, or radius divided by 7. Since the sine of 60 degrees is exactly square root 3/2, a quick algebraic cross-multiplication reveals our answer. The exact radius of the semicircle is 7 square root 3/2 units, which gives us a highly precise technical measurement of approximately 6.06 units.